So, my name is Daniel. I probably have a last name. This is Linux kernel on FPGA. If that's not what you're looking for, you're in the right place. So, specifically, I wanted to look at some of the things around speed and security, but it's also a lot easier to use FPGAs than probably anybody's actually familiar with, because that's been the biggest thing that people have given me pain about. But let's go to the next slide real quick. I've got my own slide person. Thank you, Connor. Linux has a whole bunch of abstraction layers, which are super duper awesome in that you can write fairly simple programs that do very powerful things, and not entirely factually, there's a lot of mobility around the various Linux ecosystems of things running on a lot of other things. In practice, that's really difficult sometimes, but theoretically, you can kind of use a small set of, C standard things that they get put into languages and whatnot, and just have your stuff really run on a lot of different kinds of hardware over decades. And the Linux kernel keeps that syscall to user space, ABI, very, very tight over a lot of generations, just not breaking user space. That's like their mantra. Inside the kernel, though, madness. Just absolute madness. Wars are fought. People don't die too often, but yeah. And then you've got your hardware underneath, and the Linux kernel as a thing has a whole bunch of open source drivers for almost any hardware imaginable. That's like really what the core, big, huge beefiness of the number of lines of code is all about, is driving hardware and simplifying it to just a few hundred syscalls. Nice, thanks. Next, please. This is what the kernel looks like a little bit more in depth, and there's layers upon layers inside the kernel to make things, even better.
Yeah, even better.
There's a lot of layers to make things so that people can get further and further and further down, because there's a lot of standards in here, especially like for disk and network and just everything. You can write things that are just layers inside of things in between things, and it's really, really awesome on one hand, but on the other hand, if you're actually tracing from your program to where something happened in hardware and then back out again, that's a long path, and it's entirely too much fun. Next. But that's my take on what hardware should be, is really do the thing you're trying to do very directly, and abstractions, they just get in the way. And so we're going to talk a little bit about FPGAs, and a lot of people, the first thing they say is, what is an FPGA? So I figure I'll just tell y'all real quick is, FPGAs are a whole bunch of wires and gates that get all mushed together, and some of them are really, really little to where they're like a couple dollars, and they're probably in almost everybody's cars in here, several of them. They're in Tomahawks and cruise missiles, cell phone towers, data centers. They're literally everywhere. But they're sort of the unsung heroes, because FPGAs in practice only exist because there wasn't enough demand to make an actual ASIC, to make a chip. And so FPGAs are the prototyping, sort of before you make a chip, you validate that it works as a design in an FPGA. If you've got $50 million or $100 million and you've got millions of sales, then you go and stamp out wafers and wafers of your chip, and they'll be 10% the price, 1% the price. They'll go faster. They'll be much lower power. So FPGAs are always the wrong thing to use, because they're just really not really well suited price-wise for anything, for fixed designs. The best thing that FPGAs are for is for changing. So you can change them again and again and again, potentially thousands of times a second if you were so inclined. For using for that, they're the best thing in the world. There isn't anything else like it at all, because you can make something that hundreds of millions of times a second is synchronized across its whole thing, can do so many things. It's not parallel, it's just all simultaneous. Even multiple clock domains, and They talk to network at insane speeds, line rate generally for everything, the PCI Express, memory, HBM. They do magic you cannot replicate in any other thing, unless you're making an ASIC, and you do an FPGA first. Really simply is, can an FPGA run Windows and Linux? Of course it can. The FPGA ran Linux and Windows before the CPU existed, because they prototyped running Windows and Linux on the FPGA to make the CPU. And it can run your favorite games because it was the thing their game was running on before the GPU was made, for each generation. Big, huge data centers full of FPGAs pretending to be things. So yeah, they can do anything. But that's their weakness also, is because they're very, very flexible, and they're very hard to program generally. So next one. This is a good example. It's running around the room somewhere. I hope it makes it back with me later.
It's right there.
All right, do I have somebody to run it around and show people?
It's made its way around.
Yeah, okay. You can show people if they want to see it. This one is a few $100. It's really, really awesome. It's little. The thing that makes it really wonderful is just this, is Vivado, the software from AMD that programs these, because it's a really little chip, only takes a couple of minutes to iterate on designs, which is absolutely wonderful if you're just trying to get something going quickly. It's small, it's got PCI Express, a bit of memory, it's wonderful. It's of course limited as well, but I mean, it's wonderful to make quick demos with. This one is one we've used in data centers and stuff. It's a bit beefier. It's got a lot of memory that you can put on it. It's got PCI Express, really fat. It's got a bunch of 100 gigabit things. It makes really, really fast networking stuff.
How many logical elements?
About 2 million.
Wow.
Yeah, yeah. So it's pretty nice. It takes a good hour or two to compile in Vivado, and you gotta have a lot of patience. I mean, to change the tiniest little thingy, though, you know. Next. This one's running around the room somewhere. It's is it John?
Yeah.
Yeah. So it's on John's table.
Yeah. You want me to move it around or carry it around or something?
If you want to show people, yeah, yeah, absolutely.
It's just, static and that sort of, it's probably pretty robust, right? Like.
We'll find out.
They're not shaky, right,
Yeah. we'll see what happens.
Okay.
But this one's got high bandwidth memory on it, like some of the faster GPUs do. It's also got DDR4, and I don't know why they made it the same size, but I don't get it either. It's got 200 gigabit ports on it. These little guys right here plug into SSDs, which is also on John's table.
Mm-hmm.
And so you've got NVMe, and this guy right here can literally be its own little server, whatever it is you want it to be. It can just be that. So next. And so what we've been working on is taking a whole bunch of different syscalls and just putting them onto the FPGA. And that seems like fun and everything, but you have to interface with the FPGA. There's these things called bars, which is base address registers. And it is memory space that is just mapped in, just like your DRAM and everything else. It just maps into your kernel to actually hand out to various things. And so we have the kernel just says, program A, you get this little page over here, program B, you get this little page over here, and coordinating with the FPGA will know whenever there's a write or a read to that memory space, events happen in the FPGA, and it can do things in response to that. It can itself write back to memory. It can make interrupts happen with just posted writes. But the really cool thing about it is that when a user mode program is doing that, whether it's C or Python or whatever it might be, it is just normal memory writes to the program. It doesn't know anything crazy is going on, and the kernel, hypervisor, if there's one, etc., doesn't get touched. There's no context switching at all, and so it's insanely fast. And we specifically use streaming extensions that make it so that it doesn't pollute the cache at all, because these are uncacheable writes anyway. Next. And this is a really good example of specifically what we do. Right now, this is the sort of normal path is just syscalls into the kernel controls the hardware. We just go over the whole entire thing, And this 512 is very, very important here in that on Linux, there is up to 7 registers that you pass with syscalls, and they're 64-bit. We use those and just package it in one single write. It goes right to the FPGA. And so this is sort of a diagram of the V80s in that when it gets its posted write just up this PCI Express Edge connector, it has so much memory, it's like 800 gigabit per second, that it can sit there and just pull in huge, huge amounts of stuff. Of course, doing DMA and bus mastering and things like that. It's got DDR5, which is strangely the same size for some weird reason. It is expandable to larger amounts. But with just posted writes, it has its own NVMEs it talks to, so it can decode the file system, open files, send it out the network, pull them in, put them in, and just literally this by itself in a cabinet would be its own thing all by itself. But you know, people like to use Linux for stuff and programming and whatnot, and so that's how you interface with it. Nick? Why? People in data centers like stuff to go really, really fast. Things keep getting a lot faster and more expensive, and power seems to be a concern lately, and security is a really big one. I don't know, I just like things to go at line rate. Like my own personal reasons for it is there's some beautiful platonic perfect of it goes line rate and this is the number of clock cycles and it's always that much, and that's why I'm R&D and you know, whatever business stuff be damned, I want it to be perfect. When you write a program, and it's not to dig on people that make CPUs, GPUs, etc. There's errata. There's pages and pages and pages at the end of every manual you've ever seen, and it's in silicon, and maybe it goes foof or 3.1219999 or whatever it might do, but it's something that makes people sad. There's a lot in Windows kernel, Linux kernel, etc. to fix errata. There's microcode updates to try to fix errata. And if you were an absolutely like God tier perfect programmer, your program won't run properly if there's errata on the hardware you're running it on. There's nothing you can do about that. You buy another one, every generation they put some more. Like my personal favorite instruction set ever was RTM. It's a restricted transactional memory that Intel had. Every generation, they're like, oh, it's got errata, we're going to turn it off with microcode. I buy the next generation, we're going to turn it off with microcode. The next generation, we're going to turn it off with microcode. It just broke my heart every time because it's such an awesome instruction set, but it kind of made what's the thing where the speculative execution made the. Is anybody? Spectre Meltdown, yeah. So restricted transactional memory made Spectre and Meltdown way easier. Way, way easier. That's why they kept killing it every generation. But it was also really fun. The reason why I do this is because I can just build state machines and I can know everything about them. I can put it onto an FPGA and know every little thing, clock by clock, exactly what it's going to do. And I can have certainty. The certainty by itself is worth it. If it was slower, more expensive, and terrible, and hard to program and everything, but I got certainty, that would be a good enough trade for me. Some of those things are true, though. Yeah. So, the queue here is actually kind of a little bit of a joke in that, I don't know if anybody in here has ever tried to write multi-producer, multi-consumer, lock-free, wait-free, right? Yeah? Is that kind of hard? Yeah? Well, so the joke of it is that PCI Express serializes writes and reads because it's a bus. Well, it's serial bus, but no matter how many threads you have, they always goes boop, and they go 1, 2, 3. But they're always in order. Well, some order, but they're in order. And so you get a multi-producer, multi-reader queue just for free, just from your chipset or CPU, etc. Just because all of the things are all atomically ordered. And so the FPGA just pulls them in, just happily, and then inside of itself, it can just have these big, huge, tens of gigabytes of buffers, and it just happily goes through the list of things and just sends them right back out. And when it goes back out, it's again over PCI Express, and they're all in order. It's magic. Like, just like a really, really simple thing is just making posted writes in and then reads back out with a FIFO, which is like super easy. You get the best performing queue ever and no special instructions. Yeah, it's just cheating. And so, if there's an asterisk on a slide, it's important. So, a lot of people don't use AVX 512 for anything. That's a fair thing to say. On some of the older processors, it would bring your clock down considerably. That being said, CPUs have a whole bunch of execution units, and if you send instructions to execution units you're not normally using, it is kind of free. And because these are, the 512-bit is 64 bytes, it's an entire cache line. And so when you do a posted write for it, it just goes right out, and you actually see on the PCI Express, it is a 512-bit write into the space. It happily just goes out, skips all the cache, and just, it takes no time. I've done, timestamp counter on it. It just doesn't take any time. It gets right in there with all the other instructions. If you did nothing but that, yes, it would take time. But if you have, say, 1 million of them, 1 billion of them, you do one and you say, here's the address of a whole bunch of these, hey FPGA, go figure it out, and it'll go and just pull them in at DMA speeds, which is just PCI Express limited. But probably the biggest thing that syscalls do is they flush your caches, your TLB, your store buffers, because of, meltdown inspector, etc. This doesn't do that. It doesn't interrupt your program flow. And so just one syscall in the middle of nowhere goes and brings all of your cache hierarchy back down, and you have to go and load it all back up again. And it's very understandable why that's a painful thing. As sort of a provision, though, is that syscalls are fast from a latency standpoint in that PCI Express, and I've tested on a few different things, take on the order of a few microseconds to actually get a response back over the PCI Express bus. So they're not insanely fast from that standpoint. But because they're all posted writes and they make everything asynchronous, you can do as many as you want and just have those effectively outstanding, and then go and check on them later for polling, or it can send message signaling interrupts to actually trigger context switches to select specific threads. But something that I've been partial to for a long time is Node.js, and I didn't mention it specifically in here, but Node.js moved to a promises and asynchronous sort of thing for everything, and you can have just one thread running, and it makes all these calls and everything, and just sort of waits for them all at the same time using epoll. Using this, you don't have to use epoll, of course, but using the sort of Node.js way of doing it, you can have all these things going, and they just make posted writes, and then in one spot, you can just check on them. And so it blends in very well with Rust's like Tokio.io and Node.js and Bond, and just everybody that's moving to a more event-based thing and having asynchrony built in. This is really good for that. And these are just for people to understand how fast PCI Express is going. Just some numbers on the board is, this is 2 gigabytes per second. That's the very little one that's running around. And then 3 by 16 is that bigger one. The really big heavy one that's running around right now is, it's two 8-lane things. It's bifurcated, but you add that up, it's about 63 gigabytes per second. This is not small numbers. 6 and 7 are coming. Some of the FPGAs that are next generation are going to have those. So it's going to get really, really fast. Like, really fast. We have run numbers on some stuff. We have third-party testing for some of those. They're published and they have company names and stuff on them, and we don't do that here. But the short of it is that the latency, when you're actually doing things, is none. When you're actually making posted writes, it is none. It just goes right in with your instruction stream. And you don't always have to use 512 posted writes. You can always do smaller ones. They work just as well if you've got less information to send over. These things are directly just taken from the.
It'll go back,
You
yeah.
talk too much.
I will speak slow too. These numbers are actually just taken from batching things over PCI Express. They're not controversial in any sort of special way in that just doing big, huge transfers over PCI Express is very normal. When you're doing network services, disk services, anything at all, you get the full line rate or whatever the drives, et cetera, can do. There isn't really any overhead in FPGAs because they actually just schedule out the number of clocks you need for whatever. They make it as wide as you need. It's all statically planned. And it's like a good network switch back in the old days. Like, it's just invisible. You don't notice it's there. And DPDK is probably a good example of a very similar kind of project, and that's specifically for networking. And they actually map into user mode various network cards, memory mapped I/O, and you sit there in user mode and pull, and when stuff comes in, you're immediately on it, you're doing all of your own TCP/IP, UDP, etc., and then you're telling the network card what memory address to go and pull whatever from. The network card does it. And even at hundreds of gigabits, some of these network cards with DPDK, they just go. Like line rate, they just go. This is that, but for everything. DPQ, all the things.
What is that acronym? Direct something maybe?
I do not remember. I am so bad with acronyms.
Data Plan Development Kit.
That sounds right. Like I had to look up what bar was this morning because
Yeah, because you just think.
for so long. Yeah. Yeah. The FPJ is not a lawyer, so not that bar either. It doesn't drink, so not that bar. So some of the challenges. Probably the biggest one is in multi-tenant environments, cloud specifically. Having hardware enforced things like MMUs, which has, it's another acronym that we all know what it is.
Yeah.
Nobody's gonna say.
There you go.
Having hardware actually enforce these things, but where you get to set the state machine yourself, you have auditability of the correctness of the enforcement mechanisms. And so for what we do is we depend on the kernel to set up the memory management unit to give out pages to the appropriate places, because that's something that has to be enforced by the CPU. Past that, we know every address that's written to, all the information about the process, the thread, and we can just map it to all the permissions and everything else, and all those permissions hierarchies are managed in the FPGA. And we've got abundant amount of state that we can hold in those things because it's freaking HBM and DDR, like it's a bunch of state space. And so containers are fun. This is probably insanely far more fun than containers even. Like, say WebAssembly that only can read and write to memory, that's its only observable effect, would be perfect for this. BPF, eBPF, like stuff that you can compile in kernel and run on your kernel, you can also just do that on FPGA. Like the list of things that you can do with this is just insane. The concurrency standpoint, like I don't know of a good way to say it, but some of these are 2 or 3 million lookup tables in them. They've got a bunch of DSPs and other things, but if you have a CPU and say you've got 256 threads and you're trying to get them all to do something at the same time but all separate from each other and you want to orchestrate all that, it's hard and it's maybe possible-ish, but an FPGA is like, oh, you want me to do a million different things at the same time? No big deal. Why not? Or you want to be exactly synchronized down to the clock, down to like fractions of a nanosecond? Sure, no problem. You want to have like actual things where the jitter is measured in picoseconds. Okay, like your long tail on say your web server, your database server, etc. You've got like oh these interrupts and this caching, this is just like every 4 nanoseconds it shall be. It just doesn't care. There are there are some examples out there that drive HDMI where they just calculate the color of the pixel for the pixel clock. So it's 125 megahertz or whatever. One pixel comes out and like, what do I want this pixel to be today? And it's gonna be on time every time. Show me any CPU or GPU that could do that. It's impossible. But that's the kind of stuff that we're working with. For Q, is that PCI Express does have posted write sort of credits in like the protocol of it, and so you can actually slow down that. But in practice, that's not really necessary because the posted writes are 512 bits, and just to write back an error like, hey, we can't do this, there's starvation or whatever, that's 64 bits. And so we can write 8 times as much errors as you can send requests. So it makes it effectively a non-issue. Interrupt handling is, polling is really, really fun for most everything that we do in data center stuff, because we don't care about electricity too much. But message signal interrupts are really wonderful in that you can pick the exact core that you want, you can tell it to go run this particular program, this particular thing, and the FPGA can just write to the kernel memory and even just change what things actually run and what registers are loaded with, and then tell the kernel to go do that interrupt handler. It's every kind of awesomeness, but also just terrible, but awesome. The error reporting is, we try to just use the existing, error numbers and everything that exist in Linux, because otherwise it drives people crazy. So we don't want to innovate there too much. Yeah, this says a little bit more specifically about what we're doing. I think I mentioned most of this on here. How are we doing for time?
We got plenty.
Okay. So probably the biggest part about it is that this right here, we use the 8th slot to give it a place to actually put what the response is. And so you just give it a memory location that you want to actually say, this is where the error code goes, or any additional information. The FPGA will happily go and table walk to go and see what the virtual mode address is for the physical, pull everything out. You can actually turn parsing expression grammars, etc., into state machines, and it'll go and read out very complex data structures and things like that. From the standpoint of the kernel does a lot of stuff to make things the way that drivers expect them to be, the way that hardware expects them to be. For this is, we just have the FPGA take it straight from the user and figure all that out. It's not a terrible thing as long as you have visibility into it. Yeah, probably the biggest one is the reconfigurability, just to sort of come back to it, is being able to change these while your system is running. So there's something called partial reconfiguration. These are very big chips. They have, some of them millions of different things inside of them. Being able to say, I want this portion over here to be a different thing now. You can just do that while your system's running. It doesn't disconnect from the PCI Express. There's no hot swapping or anything like that. It just does something different now. Being able to have your program in user space, make some sort of complicated thing, pass that into the kernel, pass that into the FPGA, and now the state machines just do something completely different at crazy speeds. You can do that again and again, and if you've got a large library of primitives that you really, really like, and they're already compiled, you can swap them out at PCI Express speeds. They go into the silicon very, very quickly. It's all static. And so the wires and the gates, they just remap to something new. And you can just do that endlessly. Like, you could do that thousands of times a second. Yeah, it's I love the offloading and the determinism, because that's something you simply can't get with CPUs or GPUs. Yeah. So the deployment process is actually probably the biggest one that people actually have some issues with, and so we'll go to the next slide and talk a little bit about that. So these are AMD things of Vivado and RapidWrite. So most people that use FPGAs and they go through Vivado. They give it some HDL, whether it's VHDL or Verilog, and it goes through these steps This one right here is really, really slow routing. That's just deciding where all the wires go for everything. It's very, very slow. For very big FPGAs, I've been at some conferences where people were saying some of their designs took weeks. I don't know what I would do if that happened. I would cry a lot. I cry when it's an hour. There's this thing right here, RapidWrite, and there's some people that make that, and I talk to them pretty often. RapidWrite allows you to skip any of these steps, in that the only thing you actually need Vivado for is just to make the final bit image that goes onto the FPGA. But the synthesis, place, route, and everything else, there's an endless supply of examples of, hey, I just want to put these things here and skip the synthesis. There's a contest for routing, and there's a whole bunch of participants that routed a good amount faster than Vivado. And you can just skip any of these steps, you can take things, modify them, it's just a full in and out. We use that. They have, between this and a lot of tools we use, there's a FPGA interchange sort of format. It's public and open source. And most of RapidWrite is public and open source. It's Java, specifically. We have just a lot of tools that we've been making. I write a lot of things in TypeScript and C++ and just custom domain-specific languages and whatever's fun. I'm research. It's fun. But parsing expression grammars is the thing I come back to the most. Is I want to be able to just make my semantics, make my syntax, and just make something to where I have my own proof of correctness that exactly what I wrote here is going to end up in the bit file. And so we of course synthesize things. You have to. We place them right where we want them because we have opinions about where we want things. And we've been routing on stuff, and we're doing that more and more. We're using GPUs to route, which is really, really fast, and it's also really hard. But we're getting a lot of progress there. And our hope is that we can just do all these things, jump through RapidWrite, make our bitstream images, and have it be a closed loop, real-time system, so you can just make changes on the fly. Like a really good example is Berkeley Packet Filter. Those are programs that run in kernel mode, in Linux, that people in user space write, and they're used to filter packets. eBPF does a whole bunch of other madness, which, go look it up. It's like, it is a programming, it's its own thing. But being able to just say, hey, we can take things and not run them in kernel mode, but run them in hardware mode. And it's just all the kind of fun. But this is the process that we use, and I am a very impatient person for wanting transactions to go quickly, and also for wanting cycles of my time to go quickly. And so for these is, some of these, the largest amount of time spent to make some of these iterations is just the bit generation, which takes a few seconds. These go whoop, especially when we're making small changes to the routing, etc. Something else that's really great about RapidWrite is you can change already existing bit files. A good example is that little FPGA running around. It's got maybe some number of megabytes of memory on it, and you can put what's called option ROM. And so you turn on your computer and it runs a program off the device, which is super awesome and terrible at the same time. But the ROM that you actually do that comes from the bit file, and we actually just can use RapidWrite and say, oh, these bits are here, and change just those bits, have a new bit file, send it to the FPGA, and then your time is nothing if you're just changing the program. You just boop, 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 you hit compile and just recompile and go, go, go. And it's really fast for that. And so that's one of the really great uses for it. But yeah, they're amazing guys that work on it, and they're really responsive. It's on GitHub. Thanks. One of the things that we've been looking into, when you've got queues that work very, very quickly, one of the really slow things is actually memory management in programs. Alloc and free is just the really simple part of it, but garbage collecting as well. There are some programming languages that have separate threads that do garbage collection. Now, what's really cool is if you had your FPGA doing the garbage collection, and you've got synchronization built in because of the PCI Express bus, You can have all your threads just going and allocating things all the time and complex, crazy data structures that the FPGA will be like, oh, I know how to handle that because you told me how. And it can go through and be constantly freeing these things, keeping its own reference count of whatnots, and just manage your memory for you. It's insanity. FIFO queues are really hard to do on CPUs, and that's been one of the just blindingly easy things to do on FPGAs. And it's crazy fast. We're gonna go through a few syscalls. These are like really low-hanging fruit to give just a small amount of understanding is getting your process ID, because each process has its own specific mapped pages, you can just, the FPGA, well, I know exactly who you are. It's in the address. And sends back the response very, very quickly. This is probably one that drives people really, really crazy is, I don't know if you've seen like RDC and RDRAND that you know came out in CPUs, and people are like, that's not auditable, and maybe that's possible to do shady things with. Well, FPGAs, you can make what are called XOR rings, and you plug things into themselves to where they negate themselves, but they don't have a clock with them, and so just the noise in the room, the noise in your power supply, et cetera, it makes proper true random for somebody's definition of true random. I don't know if there's truer random, but it's true. And you can put, you know, on an AES and Cha-Cha and just do whatever, but because it's open source, you know exactly what it is, and so you can trust it. And how fast does it go? How fast is your PCI Express bus? You want a really fast random number generator? That's it. That by itself's really cool for me. Clocks are sort of another one that matter to some people. Don't know why, but they seem important lately. So network time protocol, a few other things. FPGAs have really deep inside of the SerDes and then the media access layer, they actually have timing protocols in there to where they count the clock cycles, and so they can get really, really precise on packet times, especially if you've got like some good atomic clock somewhere and you've got, you know, your whole thing, you can get really accurate times from that. Some of the FPGAs, I think, the one from Bitware has a 1 pulse per second thing on it, if anybody knows what that is. And then, this got mentioned twice, it's supposed to be an E, but oven. Yeah, they're temperature controlled crystals that are very, very accurate. And they make really small atomic clocks now too.
Clock accuracy became important because of the financial trading.
Oh, so also people have been doing it with databases.
10 years ago,
Mhm.
that every financial trading had to be precise to the millisecond.
Absolutely.
I would just say you can use these for PTP, and then you're accurate to like about 1 clock cycle RMS for PTP time.
Yeah, these are places where every server in the building and in the world has to be synchronized.
You can do Syncy and PTP.
And sort of the point is, you can do a lot of these different standards and integrate them into what you're doing. This is the one that I got really excited about because I've been playing with web servers since high school, and I ended up with FPGAs because I was like, okay, let's set up Apache, and this is going pretty fast, and okay, well I can make some config file changes to make Apache faster, and that's pretty fun. And then it's like, well, the network drivers aren't super good, so I start hacking on those a little bit, and let's see what we can do in kernel mode. One of the kernel mode things is the send file. And so you can literally say, here's my file handle, here's my socket handle, go send this number of bytes, please. And it doesn't context switch back and forth, and it's really fast. It's pretty awesome. I then was like, okay, well, maybe I'll make a better network card because it wasn't doing the DMA quite the way that I wanted it to. And after I started playing with FPGAs more and more, it's like, well, I don't know what the CPU is actually for anymore because it seems like the FPGA is kind of doing a lot of this work. So doing something like send file on an FPGA is, well, the FPGA's got SSDs plugged into it, and it's got, you know, fiber plugged into it. It doesn't need me, so I can just tell it what things to send, and, you know, encryption, etc. Go send it, please. And it, I mean, you'll happily do it at line rate. Whether or not you want it that fast, another story. You can do packet pacing, which is really, really, really hard to do on CPUs. Well, this can do packet pacing down to the nanosecond, precisely. It's really fun. And so this right here, if you had just a awesome send file that you could just integrate with, Nginx and Apache and Bun and this and that, and just that by itself would make the world better. And that's one of the things I like to use it for. And there's a bunch of people that helped me with this, and everybody's really shy. But I'll mention a bunch of names that they know who they are. But I'm acknowledging them, but everybody's just really shy. So I hope I saved a little bit of time for questions. Okay.
Yeah.